All right, I want to do a quick review of the binomial distribution, and then we want to move into a geometric distribution. A student's going to guess, because they haven't studied. On a multiple choice test, each guess will be random and independent. A 12-item multiple choice test choices A through E for each item. Let X be the number of correct answers out of 12. So remember, this is binomial. It's a 12-question test, and we want to know the probability of getting a certain number correct out of the 12. So the probability that that random variable, that number correct, is 3. So this is a binomial distribution. We get 12.2, right? Because if it's A through E, you have a 1 in 5 chance of getting it correct. And 3. If you have forgotten how to type these in, I would look back at previous videos. I'm just going to write the answers for the first few of these, okay? This one, what's the probability you get none of them right? Oh, well, you'd think you'd get something right. So I would think this will be a pretty low probability. It is 0.07. The probability that X is less than 3. So now we go to a CDF. And you have some different ways to write this. I might do, because it's a whole number test, you can't get 2.5 correct. I might do the less than or equal to 2. That way you're just consistent with the notation on the calculator, because the CDF includes the number that you type in. So you want to add up the probabilities of getting 0, 1, or 2 correct. And this is actually 0.56. So sadly, pretty good chance that this student's going to get less than 3 correct. And finally, what's the probability that X is less or is greater than or equal to 4? Well, now I'm going to do a binom CDF like this, and I'll subtract it from 1, and then this will give me the probability of 4 and above. I get 0.21. So not a very good chance of doing good on this quiz through random guessing. Okay? And finally, tough, maybe I said, what's the probability they get between 2 and 7 correct? Well, maybe how I want to think about this, I'm just going to list the sample space of outcomes. So we're talking about these outcomes right here, between 2 and 7. I'm going to do a CDF of 1 and below, and then I'm going to do a CDF of 7 and below, and I'm just going to find the difference. Okay? So, again, my work, I would do a binomial CDF. We got 12.2, and X is less than or equal to 7, minus the binom 12.2, X is less than or equal to 1. And let me show that on my calculator. So there's my work. You can see I did the probability of 7 and below, and then did the probability of 1 and below, and subtracted. It is 0.72. All right, let's move on. A student is going to guess because they haven't studied, and each guess will be random and independent. Let Y be the number of questions until a student gets a correct answer. So I want you to see the difference here. A binomial setting said it's a 12-question test. What's the probability they get this many right? This is saying we are figuring out the probability that the first correct answer came on blank question. So now the variable of interest is not how many out of the total, it's the first success. How long until we get the first success? So, we'll let Y be the number of questions. I'm going to write the first one of these just by hand. The probability that Y equals 3 means this student got the first 2 wrong and then got the third one right. Okay? So like the next one, find the probability that Y is equal to 7. That means that student got the first 6 wrong and the 7th one right. And we don't need to worry about combinations and counting orders because there is only one way to get the first 6 wrong and the 7th one right. It's the one we've just written down. So actually this is called the geometric distribution. It's a little bit easier to maybe think about than that binomial distribution. There's a little less going on. Let me show you how you would type this in the calculator. Okay, so you can see I put them in. You go to the same spot, the second vars key, where there's the distribution menu, and go down to the bottom. Geometric, this is a PDF because we just want to know the specific probability that that first correct was on 3. And it's a little bit different than binomial because we don't have a set sample size, so that first number gets cut off. It's just probability and then the number of interest. And then probability and the number of interest, and there are the first two. Now, the probability that y is less than or equal to 5. And let me go back real quick and just talk about the work we'd normally put in the AP exam. So it would be something like this. Geometric, 0.2 and 3. Geometric, 0.2 and 7. So now, the probability it's less than or equal to 5. Well, now, of course, we're doing a cumulative one again. And there is, again, a menu for this where we'll go into the calculator and grab the CDF. Let's talk about y is greater than 7, meaning it takes more than 7 questions. For this one, of course, we want to know the probability that it took less than 7 and subtract that. And I'm going to go back and add a little more work here to this top one. Let me be a little more descriptive here if I can. And let's do the y is less than or equal to 5. And let me pull in those works quick. Okay, so the geometric CDF, again, just 0.2 and 5, that means it took the probability of 1, 2, 3, 4, 5 and added them all together. And of course this one would add up the probability of 1, 2, 3, 4, 5, 6, 7, and I subtracted that from 1. Now this is a little bit different than binomial because number one, obviously the big change is we don't have a set sample size, but also possible outcomes. Binomial, we always had to worry about that probability of 0. Well, we don't have to worry about that here because obviously success can only come on the first trial or later. And finally, how many questions would you expect the student to answer before getting one correct? I chose this example because I think most people can think about this and think, well, if you have a 1 in 5 chance of getting one right, well, you should have gotten one correct by the 5th, right, if you're really random guessing. And you are correct. The formula for expected value for a geometric distribution is 1 divided by the probability. So 1 divided by 1/5, of course, is 5. And we don't really talk about a standard deviation for a geometric curve, and I'll explain why in just a moment. So, geometric distribution. Each observation is a success or failure, just like binomial. All observations are independent, just like binomial. The probability of success is the same for each observation, just like binomial. The variable of interest is the number of trials. This is where it's different than binomial, because remember, with binomial, we had a set number of trials. Okay? So the formula you can see here is that Q, we typically call that the complement, that 1 minus P to the n minus 1 times P. So in our previous example, it's 0.8 to the 6th power times 0.2. That was the probability that it took 7 trials. Now in terms of shape, the general shape of a geometric PDF. So think about our example with the test, right? The probability you get the first question correct. First question is 0.2. The probability that it takes 2 questions is 0.8 times 0.2. 3 questions, 0.8 squared times 0.2. 4, this will be the last one I do, 0.8 cubed times 0.2, and so on. I point this out because the highest probability will always be on the first question, regardless of what that probability of an individual success is. So the general shape of your binomial PDF will be skewed to the right. And this is the reason we don't really care about the standard deviation. We're never going to use the normal curve to approximate this, okay? So the general shape of a geometric cumulative distribution will start, at its highest point, whatever that is, and then grow, okay? And grow, and grow, and grow. But instead of actually equaling 1 like it did in binomial, it instead has a limit of 1 as the number of trials goes to infinity. So it still maintains that kind of logistic looking shape, but the probability will never reach 1. Whereas binomial, because we had a set number of trials, the cumulative distribution was 1 at the end. Okay? So those are our shapes.